Okay, all right, so it looks like we're recording. So, more examples. We were talking about triple integrals last time. And reminder, triple integrals are pretty much it's morally not that different than double integrals. I mean, my broad sort of big picture point of view on all of these kinds of integrals that we've been talking about is chop it up, add it up. Right? So you got some domain over which you're adding up like something, right? Maybe mass, maybe mosquitoes, whatever. And the problem over the entire set is hard because maybe the density is not constant, or whatever is the resulting integrand is not constant over the entire domain. But if you chop it up into little pieces and focus your attention on each little individual piece, on that individual little piece, we say the integrand is pretty close to constant. Not exactly, but pretty close. And so on that little piece you can compute how many mosquitoes are in there, how much mass is in there, whatever it is that's associated with that little piece of the domain, and then you add up over the whole domain. Notice I didn't say anything about the nature of the dimension there. If it's a three-dimensional solid, then the size means the volume. If it's a two-dimensional domain that you're slicing up, then the size is the area. And if it's a one-dimensional domain, then the size is the width delta x that you all remember from single variable calculus. Okay, so what we're going to focus on here, what we're going to continue to focus on here today, is how do you turn the resulting triple integrals, when you have three-dimensional domains, into iterated integrals that we can actually compute, plug and chug. Okay. All right, so again, we talked about several examples last time. Continuing with examples, suppose our domain is the unit ball here in three-dimensional space. Not the sphere, by the way, but the solid in here, the whole three-dimensional ball. Okay. All right, arbitrarily, I'm going to do my slicing in this order. No particular reason. And by the way, you can think in terms of possible pros and cons. Is there any advantage to maybe slicing in one order versus the other? And I'll point out that there's just a tremendous amount of symmetries on the sphere, and it's pretty believable that, it's just pretty much not going to matter, at least from a domain point of view on this question. Okay, so x ranges from a starting value to an ending value. Keep in mind what we mean by that is that when we're doing our x slicing, this is what the slices look like. The slices, and this is hard to draw, by the way, as if you hadn't already noticed. It's hard to draw, but there are maybe bigger spheres as you start to move further back. But then when you pass the YZ plane and go even further back, the slices get smaller again, and there are these really small slices at the very beginning, and then some really small slices at the very end. But the x coordinates of those slices range from a starting value to an ending value, defined by this point and that point. And so these are the points that I want to understand. Those are the x coordinates that I need to understand to find the x bounds. And how do I understand those x coordinates? Well, we're going to play the usual game. What do I know about those points? Those points, the thing that defines those points is they're on the sphere that has that equation. Right? That's the only surface that I can at a glance look at and see that they're on. Now, this is not enough information to figure out those values of x. Right? Now keep in mind, we're looking for x bounds, so this is the outsidemost integral. I need values. I cannot just solve for x and have x be a function of y and z. X is not allowed to be a function of y and z. Y and z can be functions of x because they're further to the inside. When we get around eventually to looking at the dz integral, x will be constant, and so therefore z bounds can be functions of x. But x can't be a function of anything. So this alone, this one equation by itself is simply not sufficient for finding those bounds. So I have to ask myself, what else do I know about those points? And this can be a hard problem depending on the situation, the circumstance. In this case, lucky break, we have some symmetries. Right? The sphere, very nicely loaded with symmetries. And so I also can just see from the picture, and again, thank you, picture, I can see that those points are both in the xy plane, namely z equals 0. And again, just from the picture. You've got to have a picture to be able to make that observation. And they're both in the xz plane, namely y equals 0. Yes, you got to have a picture to be able to draw those conclusions. And this information is enough. Looking at these three equations, keep in mind we're looking for x bounds, therefore we need to solve for x in this algebra, and we can do it. Now, in fact, we can solve for both x1 and x2. It's the same algebra, pretty much, for both of these. Both the starting point and the ending point, they're both in the same sphere, same two planes. The only difference is between them, one of them is clearly positive, one of them is clearly negative, and so that determines which one's which. Okay. All right, so moving on. Now, we've got our x bounds figured out. Our x bounds are that. So we're going to then fix a value of x. The remainder of our attention on this question is going to be fixed to this x slice. We are confined to this x slice for the rest of this problem. And on that x slice now, I want to move on and ask the next question. What's the range of values of z? Again, no particular reason we could have done y or z, but having chosen my differentials in this order, you've got to go outside in for the bounds. That's very important, by the way. You got to think about the slicing process comes from the order of the differentials. So, having chosen this order, I need to look at my z bounds. Excuse me. And we got to ask, what do z slices look like? And reminder, specifically, not z slices of the solid, but z slices of the existing x slice. Right? We are again confined to that x slice here. So z slices. If I take a z slice, as I move perpendicular to the z-axis, if I take a z slice of this x slice, I'm going to get something that looks like that. Okay, so our z slices look like that. Whoops, uh-oh. Oh, okay, that's fine. And so the first slice is going to be there. My last slice is going to be there. And I need to ask myself what I know about those 2 points, because those 2 points give me my 2 bounds, z1 and z2 that I'm looking for. And again, there's some algebra that you can write down. What do I know about those 2 points? Well, I know that they're on the sphere, which has that equation. I can see that they're still in this plane y equals 0. Now again, that is a thank you to the picture. It's the symmetries of the sphere that I can see from having drawn a decent picture there, that I can see that those 2 points that determine my z bounds, they are in the xz plane, namely y equals 0. I cannot emphasize enough, you've got to have a good picture. And what else do I know? Well, I know that x has been fixed. I have a chosen value of x here. So again, you have 3 pieces of information. Here we're trying to find z bounds. So in all of this algebra here, we need to solve for z. And you get, of course, 2 values, a plus and a minus. Again, you can look at the picture and see, obviously, z1 is negative. Obviously, z2 is positive. And so you can see which one of these is which. How are we doing? Is everybody on board? All right. Okay. So, now, as usual, we now confine ourselves to a particular slice. This, of course, is a slice of our previously confined to slice. So we're going to look at this z slice of the x slice. We're stuck now on that little line segment, and on that line segment, I now want to know what's the range of values of y. Right. So, y starts there at that point. It ends at that point. Let me clean up my picture a little bit. Those 2 points have, there's a y coordinate of that. There's a y coordinate of that. I need to know what those y coordinates are. What do I know about those 2 points? Well, again, just like the previous, I can see that those points are both on the sphere. I can further recall that I've dictated already what x is, so I know what x is. X is fixed. Gosh. And I have also, of course, fixed for this consideration z. Broke my convention. So I know what z is. Again, at this point, we're looking for y bounds. Since we're looking for y bounds, we want to solve for y in that algebra. And that gives me those values. Functions of x and z, which is fine because, of course, for the y integral, for this y integral, x and z are fixed. Okay. All right, so putting all of these bounds together, having chosen that we were going to do the slicing in this order, our x bounds, color choices, right? So the x bounds are that. The z bounds were that. And finally, the y bounds were that. And there we go. There's our iterated integral. Our iterated integral that computes for us this triple integral over the original solid. Okay, how's everybody doing? Is everybody happy? Does everybody see this process? Everybody see how geometrically challenging this is? Right? So it's very important to be careful and strict with the process. Don't make there's a classic mistake that students make, which is to say, look, you can just look at the algebra and you can just kind of see how it works out. Just kind of, you don't need to draw a picture. Just look at the algebra and you sort of know this goes there, and there's sort of maybe an algebraic pattern or something, or a system to have in place. It's not going to work. It's extremely unreliable. And furthermore, it's devoid of ideas. And keep in mind, our goal here, we're not interested in getting answers. Answers are not our purpose in this class. Our purpose is to understand and communicate ideas. Right? So this picture shows what happened here and how our slicing process developed over the problem. Okay, here's another really good example of this kind of thing. Let's suppose that our domain is bounded by these 5 planes. The first thing I want to talk about is how did I get this picture out of the statement of the question. The statement of the question just gives this algebra for these 5 planes. And that's a hard geometric challenge. Right? By the way, in general, gosh, I'm so sorry. I'm making progress on this cough, but it's just not gone yet. In general, if you were to take 5 planes and ask, okay, here's 5 planes cutting through each other in some weird way, it is really hard to draw a picture that helps you understand how do they kind of intersect and what is this resulting single domain that's bounded by these 5 planes. That's terribly hard in general. And this is not a entirely general example. There's something very specific and extremely convenient about this particular example that's going to give us a foot in the door and make this actually possible. And it is that these first 3 of the 5 planes have no y's in their equation. How about that? Check it out. What are the odds? That's extremely convenient. It's not general. How are we going to capitalize on that? Well, I'm going to refer you back to chapter 12. Think about the equations of planes. And what do the equations tell you about normal vectors? What do normal vectors tell you about how the plane is oriented? It's not hard to persuade yourself because these 3 equations have no y's. The resulting planes are all parallel to the y-axis. So just think about which way the normal vector points, and normal vector is going to be orthogonal to the y-axis, and therefore the planes are parallel to the y-axis. So that makes them easy to draw. So, for example, I can first think about, well, what do these equations look like in the xz plane by itself? Z equals 0 looks like that in the xz plane, and therefore it translates into something like that. Z equals x in the xz plane looks like that, which therefore translates into something that looks like that. And x plus z equals 2 in the xz plane looks something like that, and therefore it translates into something that looks... I messed that up. Let me do that again. Oh, come on. Let me try that one more time. There we go. Looks something more like that. So those, because I know they're parallel to the y-axis, I can fairly easily draw those three planes. And now we're 60% done with our picture pretty easily. So it's a nice foot in the door. Look for opportunities to, equations that don't have one of the variables, you know that the resulting surface is parallel to that axis, and it's a nice foot in the door. Does anybody have any questions about that? Does everybody see that, how that foot in the door works? Okay. All right, and then we have two more equations to think about. Y equals 0 is, well, it's that plane right there that sort of therefore cuts through what we have, our pre-existing three planes. It sort of cuts through like that, right? And then the last one, this is a little bit of geometric challenge, but y plus z equals 3 is that's parallel to the x-axis. So you're going to just have to kind of think geometrically here, but think about how then this plane is it's going to parallel to the x-axis. It's going to kind of cut through like that, and imagine cutting through this this prism at an angle parallel to the x-axis. A little bit of geometric challenge there, but I'm going to get this out of your way. Yeah. Okay. Okay, so kind of see if I can do this decently. And slicing through at an angle parallel to the x-axis like that is going to make a diagonal cut on our prism, kind of like that. How we doing? Everybody on board? This is a hard geometric challenge, so something to think about. By the way, if you had a little trouble following this geometric argument, reminder, this is all being recorded. It's on the YouTube channel. Watch it again. Hit the pause button. Spend time thinking about it. This is an important skill to develop. Okay, so with all of those understood, here's a picture of our solid. So why I like this example, by the way, is not because it's geometrically hard, but because it's got a couple of neat features. The first feature that's interesting about this example is of the 6 different ways that you can slice up, that you could conceivably slice up this solid, most of them are bad. And so this is a great example for showing how you have to think through the order of your slicing. So for example, let's suppose that I made what we're going to momentarily see to be a bad decision, and suppose I wanted to do my dx slicing on the outside. In other words, my dx slicing first, and then whatever next. Let's not worry about those. But if I'm doing my x slicing first, I'm making cuts perpendicular to the x-axis. What happens when you take slices perpendicular to the x-axis of this solid here? And well, you're going to start off with slices that look kind of like that, and they will look like that right up until you hit this corner or edge or whatever you want to call it. At which point they start to look pretty different, right? So in other words, for certain values of x, up to that point, your slices look like that based on this back plane, right? This top edge is determined by this back plane there, which has that equation. But then for later values of x, for these values of x there, our slices look like that, and I guess they're qualitatively similar, but notice then that this top edge comes from this face, which has that equation. Right, so this is a situation we saw back in doing double integrals. Because we slice through a corner, edge, whatever you want to call it, because we slice through this corner, the bounds, the formula for the upper bound for z is going to have two different formulas, which means we're going to have to write down two separate triple integrals, which is suboptimal, undesirable. So let's not do it this way. Everybody see what I'm talking about? This is just a three-dimensional version of that same point that we talked about in the two-dimensional context. Okay, so same moral. Try not to slice through corners. So this choice here to order to do our x slicing first is bad, because in doing our x slicing first, we slice through a corner. And then likewise, what if we do our y slicing first? Do your y slicing first. Your slices are going to look like this, right? That's a slice perpendicular to the y-axis. The slices will look like that for a while, and you'll feel all well and good right up until you hit that corner. After which point, everything's different, right? After that, your slices are going to look like this, and they're going to get sort of shorter as you go along. So for different values of y, you have different kinds of slices. They're going to have different bounds for the inner integrals. Again, morally, the problem is you slice through a corner. Corner's bad. All right, so that's a bad choice too. So we really only have one good choice here, and that is to do our dz slices first. Our z slices, there we go. Our z slices start off like that, and then they get, as z gets bigger, they get like that, and then eventually there's that last slice up at the end. And you could say that, well, you start your very first slices through a bunch of corners, but you were already starting a new integral there anyway, so who cares? Right? But then you don't slice through any more corners until the very end, at which point, okay, yeah, you're kind of slicing through a corner at the end, but again, you don't care. You were going to end that integral there anyway. So there's no cost. So that's the only reasonable first order to pick. How are we doing? Is everybody on board? Yeah. Okay, so think it through. And by the way, so I emphasize here, how would we have gotten this conclusion without the picture? Right? The picture shows where the corners are. It shows where the resulting algebraic sort of problems are going to pop up. You cannot see these conclusions by looking at the algebra. And I want to point out specifically, I know some of y'all have had high school courses in multivariable calculus, and in those high school courses you may have seen some triple integrals, and overwhelmingly, I've seen a lot of examples of this of high school courses where they focus on what the algebra looks like, and they say, well, here's a system, or here's a way to kind of make reasonable guesses as to which way to slice and where the bounds are going to be, and they selectively choose their examples in such a way that will work. Right? And it just doesn't always work. So what they're doing is they're giving, I think it's very bad training. They're giving examples that only work sometimes. They have a system, that works only sometimes. And that's not good. So if you had such an experience, if you had such a high school course, you're going to have to set that aside. It simply will not work. You hit an example like this and you will not have the necessary tools to make valid reasoning about it. Okay. All right. Okay, so everything else in this example is pretty standard. I'm going to let y'all think through what these bounds are. It's just think about what bounds are determined by. Well, for example, the lower z bound is clearly 0. Right? The upper z bound is going to look like that. And just think about what is that edge determined by? That edge is determined by certain planes. And that you write down those equations, and that will allow you to determine the upper bound. It's 1, etc. Okay, it's a good practice problem. Okay. All right. Here's another example. Another algebraically I'll say, I should say another geometrically hard example. Our solid is bounded by these two surfaces. You can easily recognize that these both are paraboloids, and those paraboloids look like that, and, that. And it's a hard solid to draw. Right? It's like, I don't even know what to say that kind of looks like. It's like a weird sort of goblet turned sideways, maybe? Something like that. So the solid, of course, is what's in here. That's what we're interested in. And of course, this is where if this were a goblet, that's where the beverage would go, turned sideways. Okay. What's really hard about this is thinking about what the slices would look like. Right? For example, let's draw a z slice of this thing, a z slice, perpendicular to the z-axis, slicing through like that. Oh man, my slices would look kind of like that. It's real hard to visualize, hard to do a decent drawing of. It's just rough, right? So I'm going to make a sequence of observations about what's going to make this easy to do. The first observation I'm going to make is notice that I love solving for y in that algebra. I don't love solving for x and z. X and z would make me do square roots. I don't really like square roots. In fact, I substantially dislike square roots, because square roots in your bounds will turn into square roots in your integrand, which makes for hard integrals. So let's arrange to have it work out to our convenience that we end up solving for y in terms of x and z, and that necessitates specifically having the y integral on the inside like that. That's my first observation. My next observation is that, that means that means that my x and z bounds are on the outside. I'll remind you of an observation that we made at the end of Wednesday's class, that if I have identified which two differentials are on your outside, then you can just look at the projection into that corresponding coordinate plane. So I can look at the projection into the xz plane, and my x and z bounds will be determined by that projection. And I think it's pretty geometrically clear how to find what that projection is. That projection is defined by when this y is equal to that y, which means that I need for this to equal to that, which tells me that x squared plus z squared is 4. And so that's a real easy little double integral consideration. X squared plus z squared is equal to 4. Then my x and z bounds are real easy to write down. All right, so notice the sequence of events that led to this. I see that I want dy on the inside. As a result, I want x and z on the outside. As a result, I can think in terms of the projection to the xz plane, which makes for an easier question. Okay, so I'm a big fan of this general idea of, once you have identified what your outside differentials are, you are welcome to just project into that corresponding coordinate plane. Much easier to deal with geometrically. Now we're doing slices on a disk, super easy picture, as opposed to trying to draw these horrifying slices of the actual solid itself. So that's a hard problem, and the yellow projection is the easy problem. Okay. All right. Okay, so then resulting last question, then what are the y bounds? My y bounds, keep in mind my y bounds come from having fixed a value of x and a value of z. Therefore, my y bounds are going to come from looking at the corresponding slice. I just need to know what's the starting value of y and the ending value of y. And again, you can see that from the picture. You got to think through which paraboloid is which. Here, let me color code a little bit better. Got to think about which point is on which paraboloid, which has which equation. Think it through, right? Draw the picture. Think about your Chapter 12 techniques. But you can infer, again, from the picture which one goes where. Yeah.
Why do we have y in the inside?
Excuse me. So that was my first choice. I wanted y on the inside because I want to solve for y in these equations. Right? I don't want to solve for x in terms of y and z. That'd have square roots in it. I don't want to solve for z in terms of x and y because that'd have square roots in it. So my very first choice was, I like how y is already solved for. That means I just selfishly want to put it on the inside. Yeah. It's a choice, right? You don't have to. If you want to slice this up a really, really hard way, you're welcome to, but it's going to be a nightmare. Right? Yeah. Right. Okay, so let's see here. How are we doing on time? Oh, we're good. Yes.
If you're slicing it in that direction, doesn't that mean that the slices change from discs into like donut-shaped things? So doesn't that mean there's kind of a corner?
Oh, yeah. Well, yeah, if you were to do your dy slicing, for example, first, then yeah, it's horrifying in several ways. One is you're going to have square roots. These slices necessitate solving for y. Solving for a. When you look at the subsequent bounds, you're going to be looking for solving for z or x or something like that. But then you're quite right. We have to break it up into chunks for these values of y. My slices look like that. But then you're quite right for these values of y. Oh man, I don't know if I can draw this. My slices would look kind of like that. And yeah, so you'd have to break it up into two separate integrals, which would be, undesirable. Undesirable in many ways. Does that make sense? Is that what you were asking about?
That was, but I was confused because I thought that's what we were doing.
We are choosing to put the dy on the inside because I would like to arrange for that when I have to solve for something in terms of something, all else being equal. I don't want to be solving for x or z in terms of y because I don't want to invert those functions, right? So putting dy on the inside means that I need to solve for y in terms of x and z, which I'm happy with, but that puts it on the inside, and being on the inside, that means it's the last slice, not the first slice. Right? So my first slices, in the way I'd like to do it, I'm doing my x slicing and my z slicing first, and thus projecting into the xz plane. Yeah.
So what do those slices look like?
They're tough slices to draw, so this is where I make the observation that because I'm doing x and z slicing first, I can focus my attention on the projection into the xz plane, which is easier to draw and easier to understand. Yeah. Yep.
So to actually solve this integral, would you want it
to actually work out the from
have it be two separate ones? Or?
No, like this, you only have one integral. And, I mean, there is still a little bit of square roots in there, but at least it's not as bad as it would have been. But yeah, this is just a single integral because you don't slice through any... excuse me. You don't slice through anything. There's no qualitative changes as you slice through in this order. Yeah. Right. Okay. All right, so some physics real quick. We're going to be real fast with this. Center of mass calculations. They're just like it was for two-dimensional integrals, which I'll remind you was just like it was for single variable integrals. It's a weighted average of the corresponding coordinates. So recall that one way to write this is integral x dm over integral dm, right? Because mass is an integral. So you see that the structure of the, finding coordinates of a centroid, it's just a weighted average of the coordinates, just like it was in single variable and double integrals. It's just that now there's three such coordinates to compute instead of two, and they are now triple integrals over a solid instead of double integrals. So very, very similar. Again, it's just sort of phase one of a calculation. This is how you write a physics problem as a Riemann sum. Moment of inertia. I have a little typo in here. Apologies. That should be a triple integral, of course. Sorry about that. Same argument, though. If you look back at the argument we made about, where does moment of inertia come from? Think about, how you compute kinetic energy of a rotating object. Morally, it's the exact same calculation. It's just, you're just adding up a bunch of rotating pieces, and, the angular velocity and the linear velocity are still related by r, and everything works out the same way. So you still end up with the calculation being integral r squared dm. Just a triple integral now. And, again, it remains that what this r is depends on what are you rotating around. So if you are rotating around the x-axis, that r is, its distance to the x-axis, which is determined by that little Pythagorean equation there. Right? If you are, on the other hand, if you are rotating around the y-axis, then r is that, which is determined by that little Pythagorean relationship. All right, so please don't memorize formulas for r. For these axes, these are the formulas for r. It's a mistake. There's too many different axes. It's not just three. It's not just x, y, or z axis. What if you're rotating around a line that's neither of those axes? You've got to figure out what the corresponding distance is. There's too many cases to memorize your way through that. Right? So always interpret r appropriate to what is the corresponding axis that you're rotating around. Draw the picture. Think about in that picture what is the perpendicular distance to that axis. And solve the little Pythagorean, the corresponding, find the little Pythagorean triangle and write down the geometry. Yes?
Is the moment of inertia supposed to be a triple integral or a double integral?
Yes, right. So that it is a triple integral. That was my first little confession there. I added in purple there. I added my little third. Yeah, sorry about that. That was my bad. Yeah, totally. So the nature of the integral is dependent on the nature of the domain. If it's three-dimensional solid, then it's a triple integral. Yeah. Okay. Alrighty. Okay, so that's the little physics sort of rehash. Okay. Good news. We get symmetry theorems again. Again, I'll remind you, these might be the most important theorems that I ever used in evaluating intervals. They come up all the time. It's crazy. The world's full of symmetries. That's fantastic. Right? And so, you'd be surprised how often you just get lucky and, there's several integrals, or there's an integral that I'm doing that has several terms. I've seen it happen before that I have an integral with 5 terms in it, and 4 of them disappear because of symmetry arguments. It's really, really handy. So, reminder, we need, in order to talk about symmetry, we need to have a notion of reflection. In this case, if we're in a 3-dimensional context, we're reflecting through a plane. A reflection through a plane is exactly what you think it is. It's the point such that this line segment is perpendicularly bisected by the plane in question. Or, even easier, it's where your image is when you look in the mirror. It's exactly what you think it is. Okay. We have analogous definitions of symmetry. What does it mean for a function to have odd symmetry? It means that when you look at a reflected point versus when you look at an original point, whose reflection you're interested in, you need the value of the function to be the negative of the other. Again, it's the same idea of odd symmetry. Just 3-dimensional context instead of 2. Same idea of what it means for a domain to be symmetric. I need for whenever one side, whenever a point is in the set, I need for its reflection to be in the set. It's the Rorschach. It's a 3-dimensional version of the Rorschach type images. Okay, and we get the same theorem, the same eventual theorem. And that is that if you're looking at a triple integral, and if your domain is symmetric through a plane, if your integrand has odd symmetry through the plane, then your integral is equal to 0. Right? Two things to check, and you get this awesome slam dunk conclusion. Really nice. Okay, how are we doing? Does everybody recognize this? Familiar, right? Okay. I emphasize 2 things. They have to both apply. You'd be surprised how often I see a student say, "Hey, my domain is symmetric, therefore the integral equals 0." That's the student stepped on a landmine. You see that symmetric domain, and you see daylight. You're like, "Oh my God, this is awesome! I love symmetry," and you just want to say A equals 0 by symmetry. But if you didn't check that your function has odd symmetry, that argument alone doesn't make any sense. It just doesn't. And usually you'll not only have a bad argument, you will also get a wrong answer often. But that's, again, not the point. The point is the argument is invalid. So make sure to check that both conditions apply. And likewise, make sure that you check that these symmetries are through the same plane. Another really important one. Odd symmetry through one plane paired with domain symmetry through a different plane, useless. No conclusion at all. So it's very delicate. Again, it's a dangerous theorem to use because if you don't apply it correctly, then not only do you get a wrong answer, not only is your argument invalid, but nothing you've written down is relevant to the actual solution of the problem, and there's just no way I can rationalize giving partial credit. Very often, anyway, there's no way to rationalize partial credit. And I love giving partial credit. I really do. I know y'all love it when I give partial credit, but also I love giving partial credit, and but I just can't. So be careful. All right. Why does this work? Same reason. Morally equivalent reason to why it works in 2 dimensions. And that is, if you're looking at a Riemann sum here, keep in mind that a Riemann sum is just we're adding up a bunch of terms. And if on this piece, the term associated at a particular point, and if on this piece, come on, colors. This piece, right, at the reflected point, well, they have the same volume. If the value of the function is the negative of the other value of the function, then these 2 terms cancel in the summation. And everything cancels and you just get 0 in the Riemann sum. Morally equivalent reason. Okay. All right. Let's see an example how to use this. So this is, by the way, without symmetry, this is a brutal question. Computing a triple integral over the unit ball, which doesn't sound that bad, but keep in mind we did a slicing up of the unit ball as our first example today. Slicing up of the unit ball. Remember this one? Check out all the square roots. Why am I using check marks? These are frowny faces, right? Oh my God, look at all these square roots. Bummer. Right? Nobody wants to see. That means that these integrals, right? That first integral might be not so bad, but these 2 integrals here are going to have square roots in the integrand, and this is bad. Okay. So, right? Lots of potential for this to be a super ugly question. We're going to try to make a symmetry argument to avoid all of that pain. And in order to make a symmetry argument, I need for this function to have an odd symmetry. Let me observe that if we pick the xz plane, through the xz plane, here's the xz plane, reflection through the xz plane is given by that formula. Now I appeal to the picture. You've got to have a picture. Really helps to draw the picture. Not only will it help you keep it straight to see given a reflecting plane, what is the formula for the reflection? But it helps the grader. I know I say this a lot, but let me just remind, I think this is really important. You are communicating thoughts to the grader. It's not good enough for you to have the right thoughts. You have to communicate the right thoughts. And a picture like this makes it perfectly clear where you got this from. Right? So help the grader out. We want to give partial credit. We're looking for excuses to give you points, and this really helps us help you with points. Then notice that, with this reflection, we get a minus sign that jumps into the y coordinate of the function. And this minus sign gets squared and therefore doesn't do anything. But this minus sign, the sine function is an odd function. Sine of negative y is the negative of sine y. And so that gets that minus sign that we need. And therefore the function is odd, right, by this argument. The function has odd symmetry. And at that point, it's all over but the shouting. The domain, the domain is clearly, it's a sphere for crying, it's a ball for crying out loud, and through the XZ plane, clearly symmetric. Again, let me remind you of the rules for making symmetry argument. Well, let me get back to that in a second. And so the integral is equal to 0 by symmetry. Big win. Okay, so the rules. If you want to apply a symmetry argument in this class, I strongly encourage, unless the problem explicitly disallows it, you have to tell me what plane are you using. That needs to be indicated. You have to give me the formula for the reflection through that plane. You have to explicitly make the argument that the function has odd symmetry. And you have to state and be correct that the domain is symmetric through the same plane. All right, so all that has to be explicitly indicated in your work. Otherwise, your argument is simply not complete. And it's, again, I remind you, there's the scam, that I benefited from at least once, and I think multiple times, was there's 10 seconds left on the exam, and you're like, I don't have time to look at this integral. Okay, equals 0 by symmetry. Fingers crossed. And then, it worked. Right, so I mean, that's an idealist gain of points, and that's not appropriate. Everybody on board? Okay. Next question I want to talk about real quick. How did I know the XZ plane? How did I choose to use the XZ plane? Let's reverse engineer it, which is what I did when I thought through this question. I didn't start off. My inner oracle did not just tell me, use the XZ plane, right? That's not how it works at all. What I did is I was thinking through, how is this argument going to work, right? How am I going to, looking at the integrand, what's going to make that integrand turn negative? And it's pretty easy to see that just, think through what sort of a minus sign stuck in where would make this turn negative. And then you just notice, to make this turn negative, I need a minus sign on the y coordinate. So, said differently, from a motivation standpoint, to make that oddness argument work, that motivates wanting the reflection to look like this. And once you see that the reflection needs to look like that, that motivates this picture for what the reflection looks like, and that is what suggests that the plane should be the XZ plane. So I strongly encourage you all to sort of, think, your motivation, your thought process, very often will go in these terms. Okay. And I'm out of time. Okay, so that's a pretty good stopping point for this week. See y'all later. Have a nice weekend. See you Monday.